right, honors chemistry. Welcome to your honors lecture on Coulombic attraction. Now, we've already introduced Coulomb's force or Coulombic attraction earlier when we were talking in class about periodic table trends. And Coulomb's attraction or Coulomb's law is all about the attraction between B/W is a shorthand for between charged particles. And for us, we know that in the atom, right, in the atom, there is the proton, a positive charge, and there is an electron, a negative charge. And together, these two create an attractive, what we call an electrostatic attraction to one another. And we like to say that the protons are the pull. They're the ones kind of doing the heavy lifting, and the electrons are for the ride. All right. So we've talked about it, and we talked about how going across a period, across a row, Coulombic attraction increases. Why? Because we get more muscle, we get more protons behind that pull. And we can describe this relationship, by the way, in an equation equals Q constant times G Willikers. I'm just going to ignore that Q. Hold on. Let me start over. I'm getting ahead of myself. Force equals, or the amount of Coulomb's attractional force equals some constant times the charge value of one particle, the charge value of the other particle divided by the distance between the two particles, nuclei squared, the radius squared, okay? And so we say that when we go across a row or period, we get more muscle. So our charge values, numerically speaking, our Q values increase. We have more charge. We just have more content to go, right? But when we go down a column or group or family, however you want to call it, we notice that the distance increases due to our quantum energy levels, our distinct energy levels, all right, where electrons can exist. And we say that as R gets bigger, right, we keep on going down a row, we get farther and farther from the nucleus where the protons are, where the muscle is, and those electrons have a really hard time on the edge. Our valence electrons, our outer energy level, our outer shell electrons have a really, really hard time experiencing the pull. So we say that the Coulomb's law or Coulomb attraction decreases exponentially by the distance. And so generally speaking, we see that distance seems to have a greater effect on the Coulomb's law than charge, right? Charge is never going to be as quick for strengthening as distance is going to be quicker at weakening, okay? So that being said, when we talk about Coulomb's law, we often just compare two elements in the same row or two elements in the same column. But as honors, what happens when you need to compare two elements diagonally across from each other, where you see charge and distance, all right? And so we're going to talk about that really quickly. Let's look at carbon and sulfur. Carbon and sulfur, carbon is in, let's see, row 2, all right? And sulfur is in row 3. Now, automatically, you're thinking to yourself, oh, for sure, sulfur has a weaker Coulombic attraction because it's in a higher row. And this must have the stronger Coulombic attraction because it's in a closer or lower row, a closer energy level to the nucleus where it can experience more pull. But here's the other thing. Carbon's atomic number is 6. But sulfur's atomic number, G Willikers, is 14. No, G Willikers, 16. So that being said, now we have charge. And this would tell us that the Coulombic attraction should be weaker for carbon and stronger for sulfur. So you have to tell yourself, okay, how do these two factors, when they're affecting at the same time, okay, neither one is constant, both are changing. How do we determine which one's gonna have a stronger Coulombic attraction? I could actually give you values and you could solve for it, plug it into equation, but I'm not. I'm going to have you actually try to figure out and argue through the problem. Try to think through it. Can you make an argument on this? All right, so go ahead and take a moment to try to do that, and then we'll talk a little bit more. Okay, so hopefully you guys thought about it a little bit. And honestly, your argument could go either way. You could have decided, you know what? I actually do think carbon has the greater Coulombic attraction. And you wouldn't be completely wrong, because remember, distance does seem to have a bigger effect. So the less distance, you're removing an exponentially weakening factor, right? But if you argued sulfur, I could also understand where you're coming from, right? Because sulfur just has so many protons, it almost feels like the distance might not actually compare to the amount of proton jump, the amount of muscle you gain. So one thing I want to show you is we actually have a scale for measuring electronegativity. And I'm talking about electronegativity because remember, electronegativity, the ability to attract an electron when in a bond, right? You're already in a bond. The question is, are you going to hog the electrons more to yourself, or are you going to evenly share? Okay. So electronegativity, we have a scale for that known as Pauling scale. And Pauling scale gives a number to these electronegativity values. Electronegativity is highly, highly connected to Coulombic attraction. All trends are, all periodic trends, atomic radius, ionization energy, electronegativity. If you're in AP, you'll learn about a fourth one called electroaffinity. All of these things are totally dependent on Coulomb's attraction. And so what we see as a general gauge, okay, as a general gauge, we actually see, according to the electronegativity values that do depend on Coulombic attraction, we actually see that carbon and sulfur seem to display a similar ability to attract electrons, a similar value, a measurement, okay, a similar ability to attract electrons when in a bond, which tells us they have a similar, okay, Coulombic attraction experience within their own atom. So that's just something to think about. Like, wow, that's not a perfect comparison. It's just a gauge. It's just like, oh, well, I know these two things are connected, electronegativity and Coulombic attraction, so I can deduce or interpolate, right? I can deduce or interpolate, kind of say, oh, well, knowing this and knowing this, what might it help me understand about this, right? So there is actually no purely correct answer for this. I want you to be able to explain it though. Can you put into words your thoughts? So go ahead and try boron and phosphorus next, comparing those two. Again, they are totally diagonal from each other. You're welcome to look up Pauling scale as a general guide for, hey, that's kind of interesting. Why might that be? What might that tell you, all right, about boron and phosphorus Coulombic attraction? And I'm going to go ahead and leave it to you guys. I will write down a couple notes that you might want to consider. For example, you might want to consider, right, that boron is in row 2 and phosphorus is in row 3. Again, pretty similar situation where we have different energy levels. You also might want to consider that boron has 5 protons, the atomic number, and phosphorus has 15. Okay, and think about that. Now, I did just give you a sneak peek at the Pauling scale, and so that should get you thinking like, wait, why do we see different values? So go ahead and take some time to figure that out. And hopefully when the time comes for assessment and discussion on your knowledge, you will be able to argue. All right, good luck, guys. Bye.